optimization problems. In this section, we will study how we can use the knowledge that we have learned on the real-life problems, on the practical problems arising in a variety of areas of our daily life. For example, in business, we may want to minimize the cost and maximize profit. Okay, so in this case, we should convert the real-world problem into a mathematical optimization problems. Here are some guidelines for solving optimization problems. Okay, first, we should understand the problem first. Okay, then we may draw a picture with the variables to understand the situation properly. Then express the quantity as a function. So express the quantity that is to be maximized or minimized as a function, if possible, with a one variable function. If a function is more than one variable, then use mathematical ideas or given condition to obtain a function of one variable. Okay, at this level of your class. And also keep your mind on the domain of the function. So the meaningless solutions can be excluded in your consideration. Then determine the absolute maximum or minimum values of the function. That will give you a critical values which give the maximization or minimization problem solution. Finally, interpret your solution in the context of the original problems. That's the last step. Okay? For example, a waterway to be made so that its cross section is a trapezoid like this, trapezoid with equally sloping slide. So the angles are same, like this. The width and the two sides of the waterway are of the same as length equal to 5 meters. So this is 5 meters and this is 5 meters sideways. So what should be the sloping angle theta be chosen so that the waterway carry the maximum amount of water? So you use less money to build up a waterway that holds more waters. Okay, so we may draw the graph. We understand the problem. We may draw the graph of it, the situation. So we have a waterway like this. We have a waterway like this. Okay, we may write here and mark here as a pen. So we have what? We have a waterway like this. But this area is the same as this because we have a same theta here. So we may move this area to here to make one rectangle. Okay. Then what our problem is just finding the theta then make this area as the largest one. Okay, so we start to write it down the conditions. First, the base was 5 meters, and this is 5. So what is the area of this rectangle? Okay, which is same as the area of the waterways at a certain point. So it should be a base times height. So what is a base? Base is 5 times 5 cosine theta. 5 times 5 cosine theta will be a base. What's the height? Since this is 5 times sine theta will give us the height. Okay, so this is height. So height times a base make us 25 sine theta times 1 plus cosine theta, which is the area of this rectangle and which is the area of this waterway at a certain point. We want to maximize this area. Okay, we maximize. So we need to find the critical point first from it. If we draw this graph, we may find it in like this. And then we may find the first derivative of this function with one variable like this. If you solve this equation, then we will have a solution as theta is equal to 0 or theta is equal to pi over 3. But domain is like this. Domain is bigger than, domain is in between 0 and pi over 2. So we have one critical point, one meaningful critical point, which is theta is equal to pi over 3. That's cosine theta is equal to 1/2. That makes this 0. That's the solution of the first derivative of it. So if we take theta as a pi over 3, then the volume of this waterway will be demaximized. Okay. So if you go here, then you will see the graph. You will see the graph of where it is. You will see the graph of the here. So for example, if you draw it for copy, and we may go to the and then where we go. We copy the command for the function that we are dealing with here and paste it in here. Then we have a of theta is equal to 25 times sine theta times 1 plus theta. Here. Okay, so we plot this graph of A with respect to theta as a P, and we find the derivative of this A as a write it down as a dA, and plot that graph with the red dotted line. Then if we solve it, then we can and show these two graphs together. Then we will see the original graph of the function 25 times sine theta times 1 plus cosine theta is like this, and the derivatives of it will be appeared like this. So if we change the function, then we may have a different graph and different values. Or if we change it as a cosine, then we will do the same thing. So you can manipulate the function whatever you like to draw graph of it. So you can expect where is the critical point, where does the critical point exist. So you don't have to solve it at first. With those computational tools, you can go easily. Okay. So you can do, you don't, after you understand this mathematical formulation with those codes, all you have to do is build up the equation. That is called the mathematical modeling. Then you can easily find the derivative, you can easily find the critical point, and from the graph, you can expect to how you interpolate those computational solution to give the answer for the original ones. The second problem is like this. A cylindrical can like this is made to hold 5 liters of oil. Then what dimension will use the least metal? So we want to use a less amount of metal to build up a cylindrical can that holds 5 liters of oil. Okay? So yeah, we wanna build up an equation of what? The area. We wanna maximize, we wanna minimize the area. So what's the area? If the radius of this cylindrical cone is r and height is h, then pi r square is the area of the bottom, and we have since it's a can, we have a bottom and top and bottom, so we need 2 pi r square of the metal. And then what is the surface area except the top and bottom? That's the 2 pi r h. 2 pi r h. Okay? So this is the area. We want to minimize this area. Okay? to hold 5 liters of oil. So this the volume is 5 liters. That's about 5,000 cubic centimeters. So this pi r square h, that volume should hold 5 liters of oil. That should satisfy this condition. This gives us h is 5,000 over 5 r square. So this h can be replaced in here to make a as a single variable function. So we replace h in here to have this equation of a of r with of the function of one variable r. We want to minimize this area. So what do you have to do? Find the first derivative like what we did, isn't it? Okay. Then what? Then finding the critical point, which makes it 0. It makes this derivative 0. So from here, this should be 0. So r can be found like this, which is almost 9.2668, like this. Okay? So if you draw the graph, then this is the graph of A of r. And this dotted line is the graph of A prime of r, which is this. So as you see, this dotted line, which is the first derivative of A of r, passes through some point near 9, which is this. So we have a critical value here. If we draw the graph, it's hard to distinct. But as you see, this graph moves like this and like this, like smoothly. So you have a critical value here, which is this. So, and with this value, you can easily manipulate it like this. Okay, here I may copy it. So I copied this address, and we may leave it here. Control V. And then what do we have? We have this graph. As you see, we have the original graph 2 pi r square plus 10,000 over r. Then we plot p like this, and find the derivative same. And to draw the graph q, which is the first derivative, and solve the first derivative to find the critical point. So critical point comes up like this, and this numerical value gives us 9.2668 like this, and which is this point, which is a critical point. That has this line, this first derivative moves from negative to positive, so it should pass a certain point, which is a critical point. If we plug this value, then we will have the maximum value in there. So we can easily can tell that if we choose R as 9.2668, then H comes up from this relationship. Then if we choose R is like this and H is like this, then we will use the least amount of metal to build up a cylindrical can that hold 5 liters of oil. So now you should understand what we need is the formulation, mathematical formulation from the given condition. This kind of story problems are story problems are just can be easily handled after you write the mathematical function to deal with. Then now you have a computational tool like what I showed you. So all the others can be easily done without any burden, even though it's very hard to compute, because nowadays computer algebra systems are more and more easily accessible. So you can use it to handle, to draw the graph and to find the derivative, to find the critical point, and so you can easily manipulate the solution that you find. Example 3 says a car B is 30 kilometers directly east of the car A. So car A was here and B was here with 30 kilometers at the beginning. and begins moving with to west 9 km per hour. The car moving from here to here with 9 km per hour. And at the same moment, the car A begins to moving north at 60 km per hour to the north like this. What will be the minimum distance between the two cars? The minimum distance from 30 to it will be changed. So when will be the minimum distance between two cars? Okay. These are the problems that you have seen in at the National College Entrance Examination, SAT examinations before you got into the college. So, okay, so when that situation will be happened, find the time t and the distance. Okay, so we draw the graph from the given condition, and this was 30 kilometers. The speed of car, the car B is y, and speed of the car A is x. So we can draw the graph. Then with this x and 30 minus x, we can use the Pythagorean theorem to find the distance of L. So we can easily build up an equation for the distance between two cars like this with the Pythagorean theorem. Isn't it? Okay, then, okay, we have the formula like this. Then, first, the distance traveled can be found by the speed of a car at a certain time period. So the speed of the car A was 60 meter per kilometer. So the distance x is 60 times the time period t, and the speed of the car B was 90 kilometer per hour. So the distance y is 90 times the time period t. So we can replace x and y with this relationship to get the L as a function of a single variable t. So all you have to do is to minimize this function, isn't it? Okay. So find the first derivative of it. And solve it. Then when this first derivative of t is 0, this is equal to 0, that means t is equal to 3 over 13 hours, which means 13.8 minutes. Okay, so 0.23 hours. So when time t is equal to 23, then what happened? Let's see. This is the graph of the distance, and this is the graph of the derivative of this L of t. So we see this graph, this derivative passes through at the point near at 0.2, isn't it? So we can roughly expect the critical point is near the 0.2. So by exact computation, we have 0.23 hours. Okay, so the critical value, the minimum distance occurs at time t is equal to 0.23 hours. Then what is x? Just multiply this t on 60 to get the distance of x, and also we can find the distance of y. Okay, so the distance between two cars at this time t is, by just substituting 0.23 in here to get 24.96 kilometers. That's what we find. As you see, same thing here. Here we did the same thing. What's the difference? Nothing. Just we had to was just replace the function. Then we draw the graph P, and also we find the first derivative of it, and we draw the graph, same thing, and solve the derivative as equation 2. Then we can easily expect it. Okay, we can even do the computations on it. Okay, that's the way. Is there any question for this to dealing with this kind of problem? Okay. Next, application to economics. We consider an optimization problem arising in economic theory. Okay, this problem has to do with maximizing profit and minimizing average cost. Not just the cost, average cost. Okay. Let C of x be the cost function. C of X, of producing X unit of a certain product, then the marginal cost is the rate of change of C of X with respect to X. Okay, this marginal cost function, it can be obtained as, it can be written as C prime of X. Okay, the average cost function is this. This is all cost and divided by the number of the product. Then we have a average cost. Okay, we represent the cost per unit when X units are produced. To produce the average cost, differentiating C bar of X, which is this. So let this C bar prime of X is equal to 0, which means this the numerator is 0. That means C prime of X is same as C of X over X, which is what? The cost function, like this. Okay? Then, by the first derivative test, if the marginal cost is equal to the average cost, then the average cost is minimum. This principle is very acceptable, because if the marginal cost is smaller than the average cost, then we should produce more. Okay? Okay. Thereby the lowering the average cost. Okay. Marginal cost is smaller than the average average cost will be going down. So, okay. So let's see the examples. A company estimates that the cost in dollars of producing X items is C of X is like this polynomial. Then find the cost and average cost and marginal cost of producing 1,000 items, 2,000 items, and 3,000 items. Okay, let's find it. Average cost function is like this from here. First derivative can be found in like this. So marginal cost function is simplify just this one, which is 2 plus 0.002x. Okay. Okay. So the cost function is like this one. Okay. So we can just write. If we make 1,000 items, then total cost is just submit substitute 1,000 here, then we will have $5,600. Then just divide by it to get the average cost. But the marginal cost is only $4. Okay, after that. Okay. If you make 2,000, then average cost is $5.30, but marginal costs are increasing to the $6. It's above the average. If you make 3,000, then average cost is only $5.87, but the marginal cost is $8. What this says? Okay, so next problem. So we have made a table on cost, average cost, and marginal cost. Total cost, average cost, and marginal cost. Second problem. At what production level will the average cost be lowest? And what is the minimum, what is this minimum average cost? Okay. What to do? So as you see, we just said marginal cost is same as average cost, which says C prime of X is equal to C bar of X. So let left-hand side be the C prime of X, which is marginal cost, and right-hand side be the average cost, C bar of X. Solve it. Then we have this relationship, which means X squared is equal to, like this, so where X is equal to about 1,612. That's the point. Okay. Since C double prime of X is concave upward on its entire domain, thus the minimum average cost concave upward like this. So minimum average cost is concave upward like this. Concave upward like this. So the second derivative is concave upward like this. So minimum average occurred at this critical point, which is this. So the cost at 1,612, which is about $5.22 item, will be the minimum average cost. So if we keep those in mind to make any profit, then we should have these guidelines first to get approved the orders. Okay. Okay, here is the problems on section 4.4, and the similar problems. From the given condition, you formulate the distance with the Pythagorean theorem and find the derivatives, and and formulate the function with one variable, and then find the first derivatives and draw the graph and think about when it has a critical point, and think about the critical point by solving it. Okay, like this. This is the first derivative, and then you can easily find the critical points that give us the optimal solutions. Same thing for shop at the MP3 suppliers. We can also, the profit can be formulated in this way. So all we have to do is just find the first derivative and just the critical point to put it in. And if you draw the graph like what we did, you can solve it. We make a cost function, then to make it as a single variable function like that, and find the first derivative, and then find the critical point, and to get the optimal solutions. So you may try a similar problem that you had. So you may practice it in here, and you may use this code on other problems to deal with it. That's what you're supposed to do. So this is, so I will give you the time to explain what you solved on these sections. Is there any questions on section 4.4, optimization problems?